These are solutions to the semester exam review for Chapter 2, and let's get right into it. These first two problems, we want to make sure you understand how to identify a function by looking either at a table of values or a set of ordered pairs, and you should also be able to identify the domain and range. So domain is another way of saying the x-coordinates for a table of values or a set of ordered pairs. So the domain in this case will be -4, -1, 3, 9, and 13. The range is what we associate with the y-coordinates. So we'll make a list: 7, 12, 18, 21. Notice for repeats, there's no need to list them twice. The next thing we should do, according to the directions, is say whether or not this is a function. And the way we can tell by looking at a set of ordered pairs is we're looking to see if there are any repeats in the domain. If we have repeat x values, then this would not be a function. And so I don't see any repeats in the domain or x values, so this is a function. And then taking it further, since it is a function, how do we classify it? Would it be 1-to-1, on-to, or both? Well, to be 1-to-1, we cannot have any repeats in the range. And I notice that we do. The number 12 is matched up with two different x-coordinates. So that rules out 1-to-1. And that also rules out both. So on-to is the way we would describe this type of function. Okay, so very similar process here for number 2. The domain will be the x-coordinates, and I'm just going to write them in low to high order. It wouldn't be wrong if you didn't. -6, -3, 5, and 9. And then the range the same way. We'll start with -1, then we will go 4, 9, and 10. And is this a function? Well, once again, look at your domain and see if there are any repeats. Don't see any repeats, so this would be a function. Let's see, is this considered 1-to-1? Well, I don't see any repeats in the range, so that checks. And to be really, for it to be both, we should have unique matchups. If we think about it, a domain element produces a unique range in every case, and that works going the other way around. Every range is paired up with a unique domain element. So we actually have the both classification here. It is both 1-to-1 and on-to. All right, moving on to number 3. Here's a little word problem, again illustrating the idea of a function, domain, and range, and then we're going to finish it off with terms discrete or continuous. So Frank wants to rent a sports luxury box, and the cost is given basically by this function, y equals 10 times the number of people that attend. X stands for number of people, and plus this $125 fee, one-time fee. So the domain is basically described for us, and what this is saying, since X represents a number of people, basically he cannot invite more than 4 people. So he's going to be able to invite to attend the sporting event anywhere from 1 to 4. All right, and it goes without saying that since X talks about a number of people, that X has to be an integer. That means non-fraction, okay, and positive. Obviously, it's got to be positive to match this, but we definitely cannot have any fractions. So let's go ahead and state letter A, what is the domain and range? Well, we basically already said what the domain is. The domain, if we want to list them out, we could do, the domain would be the numbers 1, 2, 3, and 4. Those are the possible inputs, the total number of people, in other words, that he can invite. The range, again, think of the word output. Domain is input, and when you do input these numbers into this function, or substitute them in for x, what are the resulting outputs? So let's see, one at a time. If we let x be 1, we get 10 plus 125, which is 135. If we let x be 2, we get 20 plus 125 is 145. X is 3, we get 155. X is 4, we get 165. So again, this is just reiterating terminology and the fact that domain really means our input values. Range is the resulting output values. Is this a function? Well, let's see. Do we have any repeats in the domain? We do not. So yes, this would be considered a function. It's actually a line, if you think about it that way, the graph of a line that has a slope. So another way you could determine whether or not it's a function. Here's just a typical line with a positive slope, and it would pass the vertical line test. So that's another way of thinking about it. Now let's talk about these terms discrete or continuous. And the answer here is that it's discrete, but I want you to understand why. If we did, I know we're not, but if we did try to graph this function, our x-axis would represent, that's domain, remember, that would represent the number of people who attend. I think a little sketch helps you understand this term discrete a little bit better. And then the y is how much it's going to cost for that many people. So I'll just put a dollar sign over here for cost. All right, so we said that we could either do one person can go, and if they go, I'll just put 135 over here. That's if one person attends. If two people attend, it's 145. 3 people attend, 155. And then 165 for 4 people. All right, and obviously we cannot choose inputs that are between these positive integers. We've already discussed that because these represent people, and obviously we cannot have fractions of people attending. So the reason why the answer here is discrete is to be continuous, we cannot have any breaks in a line. And you notice that I cannot connect these because by connecting these dots, I'm saying that all of these inputs are allowed. And they're not, because we cannot have fractions. So that's the best answer for why is this discrete. Well, it's because this we cannot have fractions of people as inputs. That's an answer. Another answer, the acceptable answer, would be the graph of this would not be a line with no breaks. It certainly has breaks in it because we have these gaps in between the dots. So continuous would be this, where we have no breaks, and it would just continue on and on forever. Even if it didn't continue on and on forever, it would still be continuous because it's based on this particular domain. This can't go on and on forever. So this would be a continuous situation. This, however, is discrete because we have gaps or breaks in our line. All right, so that is your complete answer. It took a little bit longer to explain this, but I know when we covered this the previous time, there was a little bit of confusion on the difference between these two terms. I just want to make sure you understand. All right, so numbers 4 and 5. What makes a function a linear function? Well, number one, our variable x has to be to the first power. And other things that have to be true, we cannot have any negative exponents for x. It has to be strictly x to the first. All right, So any other exponent beside x to the first for x makes it not linear. So you're thinking, can it be written in this form where x has a power of 1? And that is true for number 4. So the answer here would be yes. It is in y equals mx plus b form. The answer for number 5 is no. There's two ways of answering this. We can't have variables in the denominator. And the reason for that is in order to have variables in the denominator, that means that x would have to have an exponent of -1. 2x to the -1 is another way of writing 2 over x. Well, that violates what we said earlier. X only can have an exponent of 1. Okay, so whether you said no variables in the denominator or whether you said x cannot have an exponent of -1, either would be okay as your explanation. So the answer here would be no. All right. Now let's talk about symmetry, and there's either point symmetry or line symmetry. Maybe a graph has both of these, or it could be that a graph has neither. And if there is point or line symmetry, we need to say what that point or line is that creates the symmetry. All right, so for number 6, well, let's start with line symmetry. Line symmetry means that I can take a vertical line and cut through this graph someplace. And the word symmetry, I know we've talked about this before, maybe you've forgotten, literally comes from a word that means sameness. Sameness. And what we mean by that is I should be able, if there's line symmetry, so for line symmetry, if it is line symmetry, I should be able to draw a line, vertical line, anywhere and or at some place in the graph and create the same image on either side of that line. Well, number 6, you can probably tell that's not going to be the case. I mean, I just picked the very middle of this graph. I drew a line straight through it. Well, the left side doesn't match up with the right side. We do not have sameness when I draw that line. So this does not have line symmetry. Now for point symmetry, you can think of it this way. You usually can go somewhere in the middle of this graph. You can think back, we're talking about cube root functions now, and we weren't talking about them at this point, but that cube root function, remember, has a turning point, so to speak, that we call an inflection point, where it's going in a certain direction and then it changes direction. Well, if there is point symmetry in a graph, that similar point exists. And you can kind of see it in this graph. This graph is coming along from the left to the right. It hits here, and then it changes, and it goes in the other direction. So we have this, what we would call an inflection point, where we talked about this in the cube root function. Well, and another way you can test for point symmetry is this. If you rotate, if you just use your imagination and pretend like this is like a spinner, and you just took the ends of this graph and you rotate it or spin it around just halfway, 180 degrees, would it put this back in its original position, or would it create sameness when you rotate? And hopefully you can see that the answer would be yes. If we spin this graph around this inflection point, we would get the same graph. And so that is a perfect example of point symmetry. And don't forget, in questions like this, if there is point or line symmetry, we need to identify the point or the line that creates the symmetry. So we need the ordered pair of this point right here, which is 0, -2. Okay, well hopefully now you've seen, since we looked at line symmetry and how this graph does not have line symmetry, hopefully you see that number 7 does. Because, and this is true of all parabolas, we can go right down the heart, right through the vertex of a parabola, and there's always a line of symmetry. We call it the AOS, the axis of symmetry. And we have sameness, or we have symmetry on both sides. They match up. It's basically the same thing. It's we could fold our graph paper on this line and they should match up with each other, these two sides. And so we have line symmetry here, and the line that creates the symmetry is the line x equals -2. Okay, remember vertical lines are always x equals lines. All right, now over here, when I draw a line, I mean, you can test some places. That's not symmetrical. Don't really see any place where I could draw a vertical line and have sameness on either side of the line. So I know line symmetry doesn't exist. I don't see an inflection point where the graph is going in a certain direction and then it gets to a point and then changes direction. Usually right in the middle of a graph is where you can find a symmetrical point, or point symmetry if it exists. But you can tell if I spin this around, you know, in that direction, you always spin it in this this counterclockwise direction. We're not going to have sameness if we turn this around 180 degrees. It's not going to produce the original graph. So in this case we have neither. All right, so hopefully those are some good examples of all three situations: point symmetry, line symmetry, and when there is neither type of symmetry. Okay, so here's a review problem with n behavior, and then we're going to state how many real zeros there are. All right, so in case you're having a little trouble seeing this, here is my x-axis. You can see it identified. The origin is right here. All right, here's my origin. Okay, so let's start with n behavior, and so we will start by traveling along the positive x-axis as x approaches positive infinity. Then where is the graph going along the y-axis? Well, as we travel to the right, positive infinity, the graph is traveling up. So y is also approaching positive infinity. As we travel to the left on the x-axis, or as we approach negative infinity along the x-axis, y is also approaching negative infinity because it's going down forever. So that is the description of the n behavior. And then state the number of real zeros. This just means, are we crossing the x-axis, and if so, how many times? Well, the only real zero we have, let me erase my origin point, we only have one x-intercept. So we're going to say the answer here is 1 real zero. So we have a number of real zeros that would match the number of times that this graph crossed the x-axis. Okay, if it crossed 3 times, which is the maximum times that this particular graph could cross, we would have 3 real zeros. Okay, so that takes care of number 9. And number 10, this is called a piecewise defined function. So it's called that because it's a function that's broken up into 3 different pieces. And let's start off with graphing each piece. Maybe I'll color code these for you. So this piece will be in red. F of x equals 8 is a horizontal line. Crosses the y-axis at 8. But we're going to restrict the length of that line so that it shows only the part of the line for x is less than or equal to -1. All right, so here is where x is -1 on the line. So I'll erase that one. And we're going to draw this in the direction that shows numbers for x that are less than -1. So that's going to be going to the left of this red dot. So let me get my line draw tool, and we'll start at this red dot, and it is colored in because it says or equal to, and we'll just draw, whoop, I should have made that a solid line. Alright, now we're ready. And that is the red piece defined by this top part of the function. Okay, we'll do this middle part, this middle piece in blue. Okay, this says we're going to draw the line 2x, f of x equals 2x, which has a y-intercept of 0 and a slope of 2. Okay, so there's a y-intercept of 0, slope of up to right 1. Pencil's not working too good. But I notice that we're only going to draw this line f of x equals 2x for these values of x. Alright, so that means from x is -1, which I have identified here, over to where x is 4. Alright, so let's keep on drawing or plotting the points for this line, but we're going to stop where x is 4. Alright, so we'll go up to right 1, up to right 1. Alright, right now I'm at x equals 2. Up to right 1, I'm at x equals 3. Up to right 1 again, and this is where x equals 4. Alright, so the blue piece is going to be defined by this line segment. Now the only thing I need to do to adjust this a little bit is, because these do not say or equal to, these end points really should be open circles. So let's adjust our dots accordingly. So this should be open. This also should be open. And we'll connect the dots in between. Okay. And it looks something like that. I may have missed a dot or two, but you get the general idea. And then finally I'll do this last piece in green. Okay, so this is the line f of x, or y, equals -4. Alright, that's our y-intercept. Minus x, so it's got a -1 slope. Alright, so here's my y-intercept, and we will count a -1 slope, which would be down 1, right 1. But notice this is called a domain restriction. We're only going to draw this line for values of x that are greater than or equal to 4. So there's really no reason to go this way at all. And I'll just start at my y-intercept and continue on with my -1 slope. Down 1, right 1. Okay, that's where x is 1. Down 1, right 1 again, x is 2. Here x is 3. And here x is 4. So really our graph is only going to show just a small piece of this line. We can just draw through those two dots. And let me get my line draw again, and we will have completed the graph part, and then we'll do the domain and range. Okay, so let's talk about domain and range. Domain will be all x such that, let's see, if we take the red, blue, and the green piece and we see how they fall along the x-axis, what x-coordinates would be involved in all of these three pieces combined, it looks like the whole x-axis is covered. Red would cover up to this point, blue takes over from there and covers from to there, and blue and green overlap. Green is going to take all of these, and so really we could say x would be, I'll show you a different way using inequalities. So we'll say that our domain is, really that's another way of saying all real numbers. It's between negative and positive infinity. Or I also showed you interval notation, which would be like this. Open brackets because infinity never stops. Okay, now let's talk about the range. What y coordinates will be used? Well, we start here at this red graph piece, and the y-axis is covered until we get down to here. Alright, so let's just write the inequality for just that part. So we have f of x such that these are all the numbers between -2, and we're not going to include -2 because it's open. And up here we have 8, and it is going to be included because it's closed. Okay, so that represents part of the range. And now the rest of our range will be all of these numbers, say 3, 4, 5, 6, 7, -8, and down. And so the way we represent that is f of x is less than or equal to -8. So these two together, these two inequalities together would represent the range of this function. Okay, very good. Now we're going to go the other way. If we're given the graph of the piecewise defined function, can we come up with the actual function? So let's see, f of x equals, let's see if we can come up with the three pieces. So I'll do this as piece number 1. Some people like to do this if you want to trace this back so that you can see what the y-intercept is. Okay, the y-intercept would be 4. The slope, if you just go from 2 points on the line, for example between these two, you go down 2 and left 2, that's a slope of 1. So remember, these are going to be y equals mx plus b, and we found out what m is, that's 1. And we found out what b is because we just kept on tracing this line using a slope of 1, and we're hitting the y-axis at 4. So for number 1, we would say that's f of x equals x plus 4. Alright, I'll call this number 2. This is another one of those horizontal lines. It's crossing the y-axis at -3. So it's basically y equals -3. Oh, I forgot to do the domain restriction, so let me back up. This is x plus 4 if our values for x are less than -2. You see how it starts at -2, not including -2, and then we just keep on going less than. Okay, so for -3, these x values are going to be between -2 and +3, and we will include those. Notice the solid circles. All right, and then finally, this last piece, number 3, a couple of ways if you want to keep on tracking this until you get to the y-intercept, that would be okay. It has a slope of left 1 up 2, actually. That's not a slope of 1. So let's see, notice how we go left 1 up 2, left 1 up 2, left 1 up 2. So that one's a little harder to determine because I don't really know exactly what that is. We know what the slope is, so we can solve for b pretty easily. The slope is, as you can see, down 2, right 1. Slope is -2. I can just take a point, and this one's pretty easy. 6, 0, 1, 2, 3, 4, 5, 6, 0 is on the graph. And so remember, I can solve for b by using this as x and this as y. M was -2. So y equals mx plus b. So it looks like b is going to be +12. All right, so I may have been able to maybe guess that, but I wasn't too confident just by looking at this dot that falls off of my graph paper. But now I know for sure where b is. And so we can write the equation. F of x equals -2x plus 12, but only if x is greater than +3. Okay, here's +3, open circle, and that takes care of number 11. All right, number 12. This is another absolute value function. They always produce v-shapes. Just think absolute value, the v in value. This is actually a transformation of the parent function f of x equals the absolute value of x. So I think I'm going to start with that. Here's the parent. Just to show you how we're actually transforming this parent function. We're dilating it by a factor of 2. This means we're going to shift 4 places to the left, and then we're going to shift 1 place down. Okay, so let's do the shift first. If you wanted to multiply the y coordinates only by 2, I guess we can do that. Multiplying the y coordinate here, or the vertex, by 2 doesn't have any effect, and so now I'm going to do left 4 and down 1. Okay, here I'm at 1, 1, but when I multiply by 2, it's 1, 2, left 4, down 1. All right, same thing for this point, multiplying by 2, left 4, down 1. And we'll just do a couple more. Multiplying by 2 makes it go to 4, left 4, down 1. And the one across from it, and you can see symmetry at this point. You can just see your line of symmetry and go 2 places to the left. And so that's an example of how to graph this as a transformation of the parent function. Now you could have also, if you forget this, you're always okay to find the vertex using opposite of b over m, comma c. I just used the translation or transformation of the parent in this case because I noticed that I truly do have the parent. There's a coefficient of 1 in front of x. So if there's any number besides 1 in front of x, you'll need to use this. You can't just go left, right, up, down. You'll have to use this to find the vertex. But coefficient of 1 means that you can just transform the original parent function. And that's your answer for number 12. 13 and 14, kind of the reverse. If you're given a function, can you write the graph of a function? Can you write the function itself? And we need to know what the parent is. So once again, this is a translation of the parent y equals the absolute value of x, but it's being moved right 1 and down 4. Okay, so the way I show a shift of right 1 is I put -1 inside the absolute value walls, and the way I show a shift of down 4 is I put -4 outside the absolute value walls. And that's the answer for number 13. Number 14 involves the parent y equals x squared. And there's actually 3 things that are happening. We've moved left 2, we went up 3, and then we reflected it over the x-axis. Alright, so the way I put all that together is, here is my shift of left 2. Here is my shift of up 3. And this reflects it over the x-axis. And so that's your answer for number 14. So you need to be able to do the transformations actually, because in some cases you're going to be reflecting or dilating in addition to shifting left, right, up, or down. You should be able to do that for any parent function that you're given. All right, and this is going to wrap it up. Describe the dilation in each function. Okay, well, first of all, let's identify the parent being affected. This is the parent y equals x squared, and when we're multiplying by a number, it's not inside parentheses, or if it were absolute value, it wouldn't be inside absolute value. If it's outside, then this is known as vertical stretch. A whole number, not a fraction, outside of parentheses. That will always result in vertical stretch. Okay? Here is the parent y equals absolute value of x, but this time notice we're multiplying by a fraction. So this is the result of, or this will result in vertical compression, making the v wider than the parent. This is going to make the u skinnier than the parent. All right, now notice we've moved the number inside. All right, so this might help you. I don't know. We've talked a lot about translations. Remember, if we have a number inside parentheses or inside absolute value, that always tells us how to shift horizontally. Well, that's the same idea when we move a factor inside. It's going to result in horizontal either stretch or compression. Okay, so I see the number inside. I know it's got to be horizontal. So my question now is, does this result in stretch or compression? Well, when the number that's not a fraction was outside, it was stretch. So when we move it inside, it becomes horizontal compression. And this is the same idea, it's just a different parent. Here's the parent y equals absolute value of x. Here's the parent y equals x squared, but again, we just took a whole number, we moved it as a factor on the inside, and so we know it's got to be a horizontal effect, and it's a whole number, so that's going to be compression. If you need a review, we did pretty thorough notes. We broke this up into 3 different days: translations, reflections, and dilations, and that was lesson 2.6. So if you want to review these concepts, I would go back and look at your lesson 2.6 notes. So that wraps up this chapter 2 semester exam review. I hope this helps you, and if you have any questions, let me know.